In Chapter 3, we're going to discover the idea of a derivative. A derivative is one of the basics of calculus. The problem of finding a tangent line to a curve and the problem of finding the velocity of an object both involve finding the same type of limit. This special type of limit is called a derivative, and we will see that it can be interpreted as a rate of change in any of the sciences or engineering. If I take a look at the tangent, if a curve C has the equation y equals f of x, we want to find the tangent line to C at some point P. So we're given our point P, and we want to find the equation of this tangent line. In order to do that, we need to find the slope of that tangent line. So what we can do is we can go ahead and take a look at some point Q. And we can compute the slope of that secant line, PQ, as the difference of its y coordinates over the difference of its x coordinates. We can find its slope. As Q is approaching P, notice that that secant line is becoming a tangent line. And if that's happening, if Q is getting closer and closer to P, then X is approaching A. So we can find the limit as X approaches A, so as X gets closer and closer to this value A, by finding f of x minus f of a all over x minus a, the difference of the y's over the difference of the x's. So let's go ahead and find the slope of a tangent line by finding the limit as x approaches a of f of x minus f of a over x minus a. If I take a look at question 1 here, we want to find the equation of the line tangent to the parabola y equals x squared at the point 1, 1. So if I look at my graph of my parabola, if I want to find the slope of my tangent at any point on this curve, it's going to be different depending on where the point is. If I take a look at a point over here, my slope is very positive and very steep, versus if I take a look at a point closer to the vertex, my slope is a lot flatter. So in order to find the slope of my tangent line at any particular point, we're going to go ahead and find our slope by taking the limit as x approaches A. A is the x-coordinate of my point. And we're going to take f of x, so x squared, minus f of a, so if I plug 1 into my equation, 1 squared is 1, all over x minus 1. Well, this works out nicely. I can go ahead and use the difference of squares in my numerator and factor that as an x minus 1 and an x plus 1, all over x minus 1. My x minus 1's are going to cancel, and I can find the limit as x approaches 1. When I plug a 1 in for my x, 1 plus 1 is 2. So that's going to tell me at the point 1, 1, my slope of my tangent is 2. Well, if I have a point and a slope, I can write the equation of my tangent line in point-slope form. And in calculus, we always just leave it in point-slope form. We never have to do anything with our line. So we're going to have y minus 1 equals my slope 2 times x minus 1. We sometimes refer to the slope of a tangent line to a curve at a point as the slope of the curve. Our derivative is going to have many different definitions. So we can find the slope of this tangent line, which is also the slope of the curve at that point. The idea is that if we zoom in far enough toward the point, the curve will almost look like a straight line. So let's go ahead and take a look at this in Desmos. If I take a look at the point 1, 1, then if I keep zooming in, notice that it keeps getting closer and closer to a straight line.